This is Neil with Anabit, and welcome to Measuring Three-Wire Resistance Temperature Detectors, or RTDs, with a Wheatstone Bridge. And that's exactly what we're going to talk about in this video. First, we'll start out with a quick overview of RTD sensors. Then we'll dive into the Wheatstone Bridge. How does it work, and why is it such a valuable tool for measuring precision sensors like RTDs? We'll see a demo of a Wheatstone Bridge and an RTD sensor in action. And then we'll talk about some of the drawbacks and things to watch out for when you use a Wheatstone Bridge circuit with an RTD sensor. Before I get started, I'll just mention check out anabit.co, where you can find other tutorials as well as open source reference designs of ADC and DAC circuits. You can also follow us on Instagram. And if you haven't subscribed already to the Anabit YouTube channel, please do that and hit the thumbs up if you like this video. All right, let's get started. Resistance Temperature Detector, RTDs, what are they? Well, they're resistance-based sensors that can be used to measure temperature and used to measure temperature pretty accurately. And so the idea is the resistance of the RTD sensor itself varies, and when that resistance varies, it correlates very well with temperature, right? So you can use the resistance measurement to calculate what temperature the sensor is in. When you look at RTD sensors, they typically have a name that starts with two letters and then with a number. So the two letters represent the metal material that's used in the sensor. So for instance, PT means platinum, Ni means nickel, Cu means copper. And then it's followed by a number, 100, 200, 500, 1,000, 2,000. That represents the resistance of the sensor at 0 degrees C. So in this video, we're going to mainly use the PT100 and the PT1000 sensors as examples and in our demo. The reason is these are the most commonly used ones out there. But what we cover here is applicable to other RTD sensors and other RTD sensor resistance values. There's multiple ways that people use to calculate the temperature from a resistance reading or a delta resistance reading from an RTD sensor. The quick shorthand version is to use 0.385 ohms, and this is for a PT100 sensor example. The more complex way to do it and the more accurate way to do it is use the IEC standard. And you can see I have the number there, and I'll provide a link in the video description. And then finally, RTD sensors come in different wire configurations, and you probably know that because that's how you found this video. 3 and 4 wire configurations have ways for you to cancel out the resistance in the wiring so you can make the measurement even more accurate. So we're going to look at the 3-wire version and how we can use a Wheatstone bridge to cancel out the effects of the resistance in the wiring that doesn't contribute to our temperature measurement. You can see a Wheatstone bridge circuit there on the left. It's basically made up of 4 resistors. We have some on the left side, which I'll refer to as the left leg. Then we have some on the right side, which I'll refer to as the right leg. And the idea is the nominal value of all these resistors should be the same. And then what we apply to this bridge circuit is VEX, or the excitation voltage as it's commonly referred to. So this should be a stable, accurate voltage value. And then what we do is we measure VO or Vout or V0 between the two nodes of resistors on the left and right side. And you can see that this is a differential measurement. That's why we're doing VL minus VR to get Vout. Now, if all the resistors have the same exact value, Vout, the differential measurement of Vout, will be 0 volts. Now, in this diagram, I'm representing R1 as our RTD sensor, right? That's why you're seeing R1 equals R0 plus delta R. Delta R is what we're interested in, right? So this is the change in resistance due to temperature. If this was an ideal circuit and the temperature was 0 degrees Celsius, Vout would be 0 volts. Okay, so we would set the resistors in our Wheatstone bridge to the same nominal value of the RTD sensor we're using. So if we're using a PT100, that would be 100 ohms. If we're using a PT1000, that would be 1,000 ohms. Now you can see on the right some equations for the output voltage of the Wheatstone bridge, the differential output voltage, and the delta R, which is the same equation, it's just some algebra and it's rearranged. Anabit has a blog post on its website, which I'll provide a link for in the video description, where I show how we come up with those equations. But you could go check out that blog post if you want more on the math of how we get these equations. So you can see that Vout equals negative V excitation. Delta R is what we're interested in if we're trying to calculate temperature from an RTD sensor. And then we have 4 times R0. And R0 just represents the nominal value of all the resistors. So if we rearrange that, we get to the value we're trying to plug into our IEC standard to get a temperature value, and that's delta R. And you can see we have the equation for that. We're going to know what R0 is. We're going to know what our excitation voltage is. So what we're measuring is V0 to get that change in resistance. Now, one key thing about using a Wheatstone bridge is ideally the excitation voltage would come from the same voltage source as the ADC's reference voltage. If we use that same voltage source on our excitation voltage, then we can do a ratiometric cancellation of the error in that reference voltage. And the idea of this ratiometric cancellation is if you're familiar with an ADC and how you calculate voltage, you calculate voltage from an ADC reading is you get a digital code, you divide that by the maximum digital code to get a ratio, and then you multiply that by the reference voltage to get the measured voltage value. Well, if you think of that equation, it's very similar to the equation for V excitation and the resistors. And so what that means is if there's an error in the voltage reference, let's say 1 millivolt or 2 millivolts, the way it works out is it doesn't matter because the calculations for the Wheatstone bridge are similar to the ADC's calculation that error essentially just drops out. So that's one of the key values of using a Wheatstone bridge is it cancels that aspect of the error out of it. The other thing is we're making a differential voltage measurement. What's nice about differential voltage measurements is you're not getting common mode noise. And what is common mode noise? Well, a short way to put it is common mode noise is just ground plane noise. So since it's a differential voltage and we're not going through the ground plane, we don't have to worry. We cancel out that common mode noise. So those are two of the big advantages of using a Wheatstone bridge. Now let's look at how we use the 3-wire sensor in the Wheatstone bridge and how we can cancel out the resistance in the wiring for making a more accurate RTD measurement. Okay, here's our same Wheatstone bridge circuit, except we removed one of the resistors and we put in the RTD, the 3-wire RTD sensor. Now, there's something important to notice that when you have a 3-wire RTD sensor, you have 2 wires coming off one end of the sensor, and then you have 1 wire coming off the other end of the sensor. And the sensor is represented as a resistor symbol. So the one alone wire goes to the excitation voltage. The other 2 wires, one goes to the lower resistor in the left leg, and the other one goes to the middle. And it's used as one of the differential measurement points. I'm showing it as VL, and then the other one is VR, right? That's where we're making the differential voltage measurement. What's important to note is that the wires for the 3-wire RTD sensor are the same length. And that's an important concept because you want them to both have the same resistance. Now, if you consider that they're the same length and they have the same resistance, notice how the differential node cuts the wires in half so that one of the wiring resistance is going to be on the top of the node and the other one is going to be linked with the R2 on the bottom. So now we've divided up that wiring resistance, and you can see I've represented the wiring resistance as RW. So R1 plus RW plus delta R is the top resistance, and the bottom is R2 plus RW. Well, if we're at 0 degrees Celsius, delta R is 0. So now that leg is balanced because the resistor on the top and the resistance on the bottom is the same because we're splitting up the wires. That resistance might be different than the right leg, but remember how voltage acts in parallel. So if the resistors in the right leg are equal, we're still going to get the same voltage drop in the middle if all resistances on one leg and the resistance on the other leg are equal. You'll just have a little different current flow through each one. So if you remember our equation from the previous slide, this really doesn't affect it, adding a little bit of resistance to the left side, as long as that resistance is equal between the top and bottom resistances. Right? So this is a way we can use a 3-wire RTD sensor with a Wheatstone bridge to cancel out that wiring resistor effect. Well, let me talk about some common issues when you use a Wheatstone bridge for the first time with an RTD sensor that you need to be aware of. So let's take an example where we're using an excitation voltage of 2.048 volt, which you'll see in our demo, that's the same reference value of our ADC that we're going to use, and it's a common reference voltage. And we're going to be using a PT100 sensor, so our nominal voltage is going to, our nominal resistance is going to be 100 ohms. So R2, R3, R4 will also be 100 ohms. If we wanted to know the resistance of this entire, bridge, we would add up the right and left legs separately, and we would get 200 on one and 200 on the other, right? And if we do a parallel combination of those resistances, we basically get 100 ohms. And the reason I'm bringing this up is because we want to know what the current flowing through the Wheatstone Bridge is going to be. So if we divide 2.048 by 100 ohms, which we're using Ohm's law, we get about 20 milliamps. Well, that 20 milliamps will be split up on either side, so we'll get about 10 milliamps per side. So why do we care about this? Well, since this is a very sensitive resistance measurement method, that type of current can actually cause heating in the resistor. And when you heat up a material and you put current through it, the resistance of that material will increase as it heats up. It will only be by a little bit, but when you're making a sensitive measurement, that little bit can matter, as we're about to see in a demo. So one downside of using a lower resistance value sensor is you get more self-heating that needs to be addressed, and you need to be aware of it. Now, you might say, well, hey, if this current's flowing through the entire Wheatstone Bridge, all the resistors are going to get the same self-heating effect. And if they're matched resistors, they'll all just increase together and cancel it out. Well, that would be true if all four resistors were the same, but the problem is the Wheatstone Bridge element is going to heat up at a different rate than your resistors. So it's this mismatch balance in the temperature drift or temperature characteristics of these resistive elements. So let me show you what I mean. Okay, here's an example setup where I have a 3-wire RTD sensor. You can see the end of the probe right here. And I have Anabit's Precision Logger, which is a board that has a 32-bit ADC. It has 5 differential channels, 10 single-ended channels. So I have it configured for a differential measurement. And it can make very accurate measurements at high resolution. And then I'm just using an Arduino Uno with SPI communication to read the value of the ADC. And then I'm using the IEC standard to calculate the final temperature. So here we go. I'm just showing a close-up of the Wheatstone Bridge. You can see the 3 precision resistors. You can see the probe right there. There's my Uno. And then we go to my computer monitor, and we can see some values printing out. First of all, notice the low value voltage measurements we're making, right? So we're looking at tens of microvolts precision here, and we can easily see those change. And if you notice, the voltage readings are all going up and the temperature is all going up slightly. This is due to self-heating. I applied the reference right before I started filming this video so you can kind of see this. Now I'm resetting the values and showing them print out again, and you can see the temperature is further increasing. Right? Not by a lot, but you can definitely see it. So that's the point is I'm using a Wheatstone Bridge, but because of the current value, I'm actually affecting the measurement. So that shows the downside of self-heating, especially when you're using a lower resistance value RTD sensor. The other thing I want to mention is most reference ICs, or at least the ones I've worked with, can't put out 20 milliamps. So what you typically have to do in your design is add a precision buffer amp and then feed the ADC and the Wheatstone Bridge from that precision buffer amp to get that ratiometric cancellation. But of course, adding a buffer amp adds more cost to your design, and you still have the self-heating problem. That's why it's pretty valuable, in my opinion, and why I typically use PT1000 sensors, because they have a much higher resistance, so you get a much lower current flow. In our example, we'd get 2 milliamps, which leads to less self-heating. Now, of course, though, there's some ways you can deal with self-heating, right? You can oversize your resistors, which I did for this design. I'm using 1206 size resistors that have pretty good power handling capabilities. So the larger the power handling, the less susceptible they are to self-heating. You can also add active cooling. And then finally, another trick you can do is just use a lower reference voltage, right? The lower the reference voltage, the lower the current is going to be flowing through the Wheatstone Bridge. But of course, then the V out value is going to be much lower. And as you can see, it's already low in the example I just showed. So with that said, let's see an example of a PT1000 in action. And we're going to be able to see how accurate it can be, as well as how fine its resolution can be when you combined it with a high resolution, high accuracy ADC and a good Wheatstone Bridge that's not going to have self-heating. Here we have our same circuit, except now I replace the Wheatstone Bridge with the same design as the Wheatstone Bridge you just saw, but now I have 1,000 ohm precision resistors instead of 100 ohm. And then I have a 3-wire RTD sensor that's a PT1000. So we went up to a higher resistance. You can see my excitation voltage is connected directly to the board. So this is where the board outputs its reference voltage that the ADC uses. So for this measurement, I'm going to get the ratio metric cancellation, and I do a short calibration of the ADC to eliminate offset voltages. So I'm really priming my circuit to make a very accurate measurement. And you might see this glass of ice water over here. So I have this sensor as well as a reference sensor that's connected to my DMM in this ice water. And the reason I went with this ice water is because I found that me breathing on the setup or the exhaust from my computer would change the sensor values because these sensors are set up to be very sensitive. And because the sensors are a little bit of different construction, one would heat up or cool down faster than the other. So what I found is if I put it in liquid, it works better for this demo because I get a nice stable reading. Okay, there's the Anabit precision logger. There's the Wheatstone Bridge connected to the voltage reference. There's my Arduino Uno. And then there is the glass of ice water. Now here, what I'm doing is I reference measurement, so you know I'm not just using smoke and mirrors, but I have a 5K thermistor sensor connected to my very high precision DMM. And I'm making a long measurement time, 100 power line cycle measurements to get a very accurate thermistor measurement. Now, the point is I'm not saying this thermistor measurement is more accurate than our RTD measurement. I'm saying the RTD measurement is probably more accurate, but I just wanted to show you a reference besides just the RTD measurement. So we can see about 4.6 degrees C. So now let's go over to my computer, and we're going to see some measurements start to print out. If you notice from the other demo, the measurements are taking longer to print out. That's because I'm doing a longer averaging time and more filtering with my Sigma Delta ADC. Okay, I'm going to pause it right there. So notice that the measurements, first of all, are almost exactly the same as what you saw on the DMM. So that's a good correlation for a reference. And we can see we're getting that very high precision. I have even higher precision set on these measurements, so we can see down to the microvolt of this measurement. You might notice, hey, these values are actually going up. Is that self-heating? It's not self-heating because what I did is I turned this on. I let the board sit and make measurements at room temperature. Then I put them in the ice bath. So everything has stabilized, and we shouldn't see much self-heating at this low current flow. So what we're actually seeing is actually the water slowly warming up. And it's doing it very slowly, but it's doing it in a very consistent basis based on the temperature in that room. So the idea is you can see the temperature slowly going up from the water warming up. So not only were we making a very accurate resistance measurement, but we are getting very good consistent resolution because we have very low noise in this measurement. Okay, lastly, I want to end this video with just some comments on the ADC and your measurement circuit. So this was focused on the RTD sensor and the Wheatstone Bridge especially, but of course we need an ADC circuit to measure it. You could check out the precision logger, which has everything you need to make an RTD measurement if you're unfamiliar with ADC designs, and it's an open source board. What I'm showing here is based on the delta V, which is a conversion of the delta R, and our voltage reference, a per degree voltage change is about 1.97 millivolts, right? So you need at least tens of microvolts of resolution to make a very accurate or very high precision measurement. And here I kind of show, well, if we had ADCs that are 18-bit and 16-bit with the same reference, this is the type of resolution you're going to get. But what you have to be aware of is what's the difference between resolution and useful resolution? And useful resolution is often referred to as ENOB, effective number of bits. So if we have too much noise in our measurement, some of these bits may jump around and you can't get an accurate measurement. Resolution is only useful if you have enough accuracy to back it up. So that's what I'm trying to show there. If you don't have access to a high resolution ADC, like on the precision logger, or you need to keep costs down, you could use an amplifier, specifically a instrumentation amplifier with a very high gain, right? And what's nice about the Wheatstone Bridge is the measurement is centered around 0 volts, right? Once you're at 0 degrees Celsius, you just go up in voltage or down in voltage. It's easy to provide a high gain to that value since it's centered around 0 rather than it being centered around 1 volt or 2 volts or something like that. So you can easily apply a 10 or 100 times gain to that voltage, and then an ADC with a lower resolution and maybe not as great accuracy can be used to measure it. And then another thing to realize is calibration, right? You can get rid of error in your ADC by doing a simple 2-point calibration, which I have a tutorial on, a video and a blog post on anabit.co. That's it for measuring 3-wire resistance temperature detectors, or RTDs, with a Wheatstone Bridge. If you have any questions or comments to add, you can use the comment section below, or you can head to the anabit.co where we have a forum for data converter discussions. Thank you for watching.